Okay, so we have spent the last few weeks talking about forces and developing the ability to analyze forces and understand what happens when the net force on an object is zero and what happens when the net force on an object is non-zero. And now we want to shift gears slightly, and we want to start to think about motion, changes in motion, applying forces. We want to start thinking about all of this in a slightly different way. And the title of this next chapter is Work and Energy. So we're going to start thinking about these new concepts, something called work, and then this idea of energy. So to start, let's just look at this pink highlighted text here. What happens when a net force is applied to an object? Well, the object accelerates, right? And so that's what we've learned from our force analysis. And so if you can determine the net force, then you can immediately determine how the motion of the object changes, because you can determine the acceleration. But in blue here, I've got written that there's another way to characterize what's going on, and the way that we're going to characterize what happens when a net force is exerted on an object is we're going to start talking about this quantity work. And so here's my example. I've got a block here on the ground, and let's say that there's no friction between the block and the ground. And I begin to push to the right. So there's a net force to the right on this block because there's no friction between the block and the ground. And so I push this block all the way over here. The entire time I'm applying this net force. So I've applied this force, and the block has traveled some distance. The position has changed. And the question is, well, what happens to the block? Well, we know from force analysis, the block must be accelerating as it's moving from left to right. So it'll be moving faster over here than what it was moving over on the left. And so we can define a new quantity, and we're going to call it work, that's related to the force that I'm applying to an object and multiplied by dr, the small chunk of displacement. And then this integral means that we evaluate this over the entire motion. Now, the multiplication here is this little dot. This is known as the dot product, and so I'm going to ask you to go review the vector multiplication video and notes, because f dot dr, the way that the dot product is defined, is that this product is equal to the magnitude of f times the magnitude of dr times the cosine of theta, and theta, if you look at my picture here, theta is the angle between those two vectors. All right, so this is called the dot product, or sometimes called the scalar product. When you multiply these two vectors together in this way, you end up with a scalar quantity. All right, so we're doing the dot product, and then we're integrating that to figure out the total work done by the force being applied to the object. So a few things to note, that if the force that's being applied is a constant value, then this integral becomes sort of trivial. F is constant, so it comes out of the integral. If you just integrate over the change in path, you just get the displacement, delta r. And so if the force is constant, then you just get the magnitude of F times the magnitude of the displacement times the cosine of theta. Remember, theta is the angle between the force and the displacement. So some things to highlight here: work or energy, the same idea. These quantities are scalars. Right, so we took a vector and another vector, we multiplied them together, and we got out a scalar. That's because we're multiplying them together with the dot product. So work, energy, that's a scalar quantity. Now, it's a scalar quantity, which means there's no direction associated with work or energy, but there is, of course, a unit. And the unit we can think of just by looking at the product here. I'm multiplying the magnitude of the force with the magnitude of the displacement. Well, remember, force is a Newton, and the displacement unit is a meter. So a Newton meter is the unit for work or energy, and we use energy so much. Energy is such an important quantity in physics that we call this unit Newton meter. When we're dealing with energy, we call that unit a joule. So 1 joule equals 1 Newton meter. So go back to my example. I am pushing on this block. There's a net force to the right. The block has moved through some distance. There's some displacement for the block after whatever time interval this is. So if work is done on an object, what happens to the object? Well, the object speeds up or slows down. In this particular example, the net force is to the right, and let's say that this block just starts at rest. Net force to the right, the object's going to be speeding up as we move to the right. All right, so if work is done on an object, then the object speeds up or slows down, and that is a nice segue into the first type of energy that we're going to talk about, and that is kinetic energy. And kinetic energy is energy associated with motion. So if an object is moving, it has kinetic energy, and kinetic energy is defined as 1/2 mv squared. So 1/2 times the mass of your object times the square, so squared the speed of your object. So again, kinetic energy is energy, so this is a scalar quantity. There is no direction associated with kinetic energy, and in fact, all of our objects have positive mass, right? There's no such thing as negative mass, and v squared is always a positive value, and so kinetic energy, the smallest kinetic energy value you can have is 0. That would be when the object's not moving, and otherwise, kinetic energy is always positive. So let's just look at a few examples here. I've got 2 objects, mass of 2 kilograms, mass of 5 kilograms, and they're both moving with the same constant velocity of 3 meters per second. So what's the kinetic energy for the 2 kilogram mass? Well, just plug in the values. I get 9 kilogram meter squared per second squared, which seems like an odd unit, but if you remember that a Newton is a kilogram meter per second squared, this is really 9 Newton meter, which is 9 joules. So now let's look at an object that's more massive, right? 2.5 times more massive, moving with the same speed. What's the kinetic energy of the 5 kilogram object? So 1/2 mv squared, we end up getting 22.5 joules. So we increase the mass by 2.5 times, we increase the kinetic energy by 2.5 times. Now let's look at a different example where I've got 2 objects with the same mass, but now they've got different speeds. So in this case, object A has a 2 kilogram mass but a speed of 2 meters per second. So what's the kinetic energy? 1/2 mv squared. So we get 4 joules for object A. What about object B? Same mass, but now 3 times the speed. So 1/2, 2 kilograms, 6 squared, so 36 joules. So we increased the speed by a factor of 3, but since in kinetic energy that speed is getting squared, we've actually increased the kinetic energy by a factor of 9, 3 squared. All right, so that's the idea of kinetic energy. And what we really care about in energy analysis, and we're going to start talking about this now, is what we care about is how energy changes over time, whether it be the types of energy that an object demonstrates or possesses, probably isn't the right word, but the energy associated with the object, how that changes with time, and if the total energy of an object changes with time. Those are questions that we want to investigate. And so we're going to start that investigation by connecting work and kinetic energy. So if work is done on an object, then the kinetic energy of the object changes. Right, so if you do work on an object, the object will speed up or slow down depending on whether you're doing a positive amount of work or a negative amount of work. So take, for example, I've got an object moving through point A, and at point A, it's moving to the right with some velocity, and then I apply a force to the right, and of course, sometime later, the object's going to pass through point B. Well, since my force is in the same direction as the displacement, that's a positive amount of work that I'm doing. The kinetic energy of the object will increase. Notice how I've just, same object, so it's the same mass. So if the velocity vector is bigger, it means that the kinetic energy is larger. So the work energy theorem is how to connect the work that you've done to the changes in kinetic energy of your object. So if you do work between 2 points, so points A and B, if work is done, then that is equal to the change in the kinetic energy of the object. So that is, compare the kinetic energy at B to the kinetic energy at A. So if you take the difference in the kinetic energy is equal to the net work that has been done on your object. And so if the final kinetic energy, B, is greater than the initial kinetic energy at A, then a positive amount of work has been done. This difference will be positive. If the final kinetic energy is smaller than the initial kinetic energy, then that difference will be negative, and a negative amount of work will have been done on your object. So that's the idea of either speeding up or slowing down. Now, the last thing that I want to mention in this video is just the idea of power. So we've all heard of the word power, but we've got a very specific meaning in physics for what power is associated with. Power is the rate at which work is done. So that's sort of a fancy way of saying it's the derivative of work with respect to time. So it's the rate at which work is done or energy is produced. And so the simplest example I can think of this to demonstrate this would be comparing like a Prius and a Ferrari. So a Prius and a Ferrari have pretty much the same mass, about 3,000 pounds, but a Prius goes from 0 to 60 in just about 10 seconds, a little over 9 seconds. But a Ferrari goes from 0 to 60 in about 3 seconds. And so after the 10 seconds or after the 3 seconds, both cars have the same kinetic energy, right? If they started from rest, their initial kinetic energy is 0. At the end, they're both moving at the same speed, and they both have the same mass, so that means 1/2 mv squared will be the same. So the amount of work done in each case is exactly the same, right? The total change in kinetic energy is exactly the same. So the dW part would be exactly the same. But the Prius, it takes 10 seconds for that to happen, while the Ferrari takes 3 seconds. So that means the Ferrari is essentially 3 times more powerful than the Ferrari in this scenario, because it takes a third of the time to deliver the work or produce the energy of changing the car's kinetic energy from 0 up to whatever the kinetic energy is at 60 miles an hour. Right. So the change in energy, the change in the kinetic energy for both cars is exactly the same. The Ferrari does it in a much smaller amount of time. So we would say the Ferrari is more powerful, or 3 times more powerful than the Prius.